This example is starting us off with an equation, and they want us to determine the slope of the tangent line. The language slope of the tangent line, that is always telling us that we need to go ahead and find our derivative. We're looking to find our f prime of x. More specifically in this problem, we'll be looking for our dy dx. Remember that derivatives give us the slope of the tangent line. That's the equation we use for finding slopes when we're in a calculus class. And then they want it at a specific point, 1, 3. So that's an x value and a y value right there. So in order to find the slope, we need to find our slope equation. We need to find our derivative, our dy dx right now. As we come to look at our specific problem, what we're going to notice here is we've got this x cubed plus y squared equals x to the 5th times y to the 4th. For the first time ever in this class, you start seeing x's and y's sort of what I call commingling within the problem. So previous problems to this, you were used to seeing a nice clean y equals 13x to the 5th. Maybe you had some crazy stuff going on inside there, but there was at least a y on one side and all our x's were over on the other. And we found the derivative pretty straightforward. Here, this is going to be a derivative again, but now we need a new process, and that new process is referred to as implicit differentiation. So to find our derivative, we are going to wrap this thing in a set of parentheses, and we are going to ddx this equation. We're going to take the derivative with respect to x right now. And that's because what we're looking for is dy dx, and so that tells us what we should be using on the bottom here. When I do implicit differentiation, I've got a little saying that I use, and that goes, every time I take a derivative, I get extra stuff. So every time we take a derivative, we're going to get extra stuff. And what that extra stuff is going to look like is kind of envision there being this little box behind that d on top. And we're going to fill that box in every time with the letter of whatever we took the derivative of, and then over dx. So what that looks like in practice here, we would come through and we'd say, okay, I'm going to ddx this. So the derivative of x cubed would be 3x squared. We took the derivative of an x, and so what we're going to get out of here is we're going to get dx over dx. We filled that little box in with an x. And now we just keep moving on through the rest of this thing. So we take the derivative, we get plus the derivative of y squared would be 2y. Took the derivative of a y this time, so we get dy dx, filling that box in with our y right there. And then all of that is going to be equal to, and we have to take the derivative of this. And what we're looking at here, we have x to the 5th times y to the 4th. So as you're doing implicit differentiation, remember that chain rule, product rule, quotient rule, all these rules still apply. So what we're looking at here is two things being multiplied, which means we need to apply the product rule. So my product rule saying that I use goes f g prime plus g and then f prime. And when you're doing implicit differentiation, remember that as you do this process, it's only when you go find that g prime and the f prime that you are taking a derivative and you get your extra stuff out of there. So I'll come back over. I'll label x to the 5th is going to be my f piece. Y to the 4th is going to be my g piece. And now we just follow our product rule recipe. It says first go grab f. So we just go grab f untouched. Then they want us to take the derivative of g prime. So we take the derivative of y to the 4th. That would be 4y cubed. Took the derivative of a y, so I get my extra stuff. I took the derivative of a y, so I get a dy dx. Then we get plus from our rule. Go grab the g piece. So that's y to the 4th. And then we're going to multiply that by f prime, the derivative of f. So we're taking a derivative, the derivative of x to the 5th, following the power rule. That's 5x to the 4th. Took the derivative of an x, so we get a dx over dx, filling that box in right there. At this point in the process on an implicit differentiation problem, I call the next step just a cleanup step. Really, you just kind of want to run through this at first and put all the pieces in as you come across them. And now what we want to do is kind of make it more user-friendly because we're about to have to do some algebra on it. So working our way through this thing left to right, I have 3x squared dx over dx, that's like having 5 divided by 5. Those things cancel each other out. That's just a 1 right there. So then plus 2y dy dx equals, rearrange this stuff to make more sense, which is just numbers and then alphabetical order. Then we've got a dy dx on that piece. Plus, bring all that together, we get 5x to the fourth, y to the fourth. Again, numbers and then alphabetical order. And again, at the end here, we have dx over dx just cancels out. Keep in mind that the long game here, what we're really trying to do, right, is we're trying to find dy dx. We're trying to find a slope equation so that we can find our slope of the tangent line. So what that means is we need to solve this equation to get dy dx by itself. Whenever you run into this type of little algebra situation where you've got multiples of what you're trying to solve for, so we've got multiple dy dx's and we need to get it down to just one. The algebra trick for this is always the same. You want to get everybody that has a dy dx, every term that has a dy dx on one side of the equals, and anything that doesn't have a dy dx, move it to the other side. So separate these out into things with dy dx's and things without dy dx's. It doesn't matter which way you go. I'm going to move the dy dx's left and the stuff without dy dx's to the right. So I'm going to move the 3x squared over to the right, and then I'm going to move this 4x to the fifth, y to the third, dy dx over to the left here. So 4x to the fifth, y to the third, dy dx. So then cleaning that up now, the 3x squareds cancel out. We end up with 2y dy dx minus 4x to the fifth, y to the third, dy dx equals, that stuff cancels out, and then we have 5x to the fourth, y to the fourth, minus 3x squared. The reason that you do this every time and why this works now is because now that everything on this side of the equals has a dy dx in it, we can factor a dy dx out of everything. So we can pull a dy dx to the front, leaving us with 2y from that first term and then 4x to the fifth, y to the third from the second. So now we've gotten multiple dy dx's down to just one dy dx, which is going to make our lives a heck of a lot easier. And then this right side just stays the same. The next move here is we just need to get dy dx by itself, so we're just going to divide both sides by this chunk. So divide by 2y minus 4x to the fifth, y to the third. And out of there, we get our slope equation. Dy dx equals 5x to the fourth, y to the fourth, minus 3x squared over 2y minus 4x to the fifth, y to the third. And so we now have our slope finding equation. So this is going to tell us the slope at any specific point that we want to find it at. In this problem, we are going to be specifically asked to find it at the point 1, 3. So that's our x and that's our y. And so now we're just going to take those values and plug them into our derivative. You would say dy dx evaluated at the point 1, 3. And so we're just taking and we're plugging x and y into this equation here. So everywhere I see an x, I put 1. Everywhere I see a y, I put 3. So we get 5 times 1 to the fourth times 3 to the fourth minus 3 times, that'll be 1 squared, over, and then 2 times y is 3, and then minus 4, x is 1 to the fifth times 3 to the third. And so from there, simplify it by hand if you can, put it into your calculator if you need to. Whatever you got to do at that point, that's just like a little numbers game. So I'm just going to quickly kind of start putting this together. The ones go away here. We end up with, what is that? 3 to the fourth is 81. And so we are going to end up at the end of all of this with negative 67 over 17 if we put all that together. So the negative coming from the bottom there. So this is our final answer. That is the slope of the tangent line. We used our formula and popped that into our calculator at the point 1, 3. If they want it at a different point, you just plug it in. This formula here works for all points that you need off of that specific equation. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.